Good morning. Welcome to an invited talk in the Taming the Data speaker series. This series has been made possible by generous support from Cisco, EMC, Informatica, SAS, ePartners Program, and the NC State Engineering Foundation. Today, it is a pleasure to introduce Dr. Flavio Villanustre, who will tell us about solving big data problems with the open source HPCC systems platform. Dr. Villanustre is the Vice President of the Technology Architecture and Product for LexisNexis and leads HPCC system. And he also has a colorful past, it seems. And he has been supporting open source products for a number of years. And he will tell us about the big data analytics with the platform.
Thank you. Hello, everyone, and thank you very much for having me here. It's a real pleasure to collaborate with NC State, and it is beyond me. We have a number of other initiatives with NC State. We are trying to build up into the industry academic collaboration as well. So there are a number of initiatives within our company, and I will speak a little bit about the company just to give you an idea, a flavor for what we do, but I will focus on the technology. This is not a presentation on LexisNexis necessarily. But as a company, we are part of a larger organization called Reed Elsevier. Many of you might have heard about Elsevier, which is one of the largest worldwide publishers of scientific data, journals, and papers and books. And we have other 4 business units in that company. One of those is LexisNexis Free Solutions. We provide data services and analytics for corporate customers, for the most part in the US, but we also have now some presence internationally as well, and we are growing internationally. And the other 3 business units are Reed Business Information, which provides analytics solutions to oil and gas industry and some marketing solutions as well. Reed Exhibitions, which organizes some of the exhibitions around the world, like Comic-Con, that's one of those. And LexisNexis Legal and Professional, which provides data services and analytics services to attorneys, for the most part. They manage a significant pool of data on case law, news, patents, and other data that attorneys leverage. Very good. So, but I want to make this presentation a little bit more interesting than just going through and drilling down into the technology. And we can go as deep as you want. And please feel free to ask questions at any time. But I will start with some applied aspects of our technology. And then I'll explain how it got developed and what it is about. But let's take a look at a few examples. This one, for example. See? This works? Does? Very good. So one of our large markets is the insurance industry. We host a number of contributory databases from the insurance industry in the US. Every insurance carrier in the US contributes data to our contributory databases. We collect all this data, aggregate it, link the data, and provide back services on this data to these insurance carriers. So if you you have a car and you're insuring your car with any company in the US, that data will be in our databases, and it will be used to, for example, provide a good idea of risk that you represent to insurance companies so that they can quote appropriately the price for your next insurance quote. If you have an accident, the risk increases, so they are probably likely to charge you more, despite which insurance carrier you had the accident with and which one you are trying to get a new quote from. They all leverage the same database. But as part of that, it is not just about the quoting process. There is an important component, which is detecting fraud by leveraging that data. This, in particular, is data about car accidents. Each one of these capital A's represents a claim, an accident in a southern state in the United States. When you look at this, every one of these claims has a number of actors that are involved. These are people or other assets that have been damaged by the accident. And all of them seem disconnected. Yeah, there are a couple of them that are connected in some way here because they have some people that are perhaps co-owning some other car or something like that. But for the most part, they seem like random cases of accidents, and eventually the adjusters pay these claims because they seem like normal claims. But this shows a little bit of what you have a partial view of things. And this goes far beyond the fraud detection. But in fraud, there is a class of fraud, which is a social network type of fraud, where you can retrieve additional information, but knowing the structure of the social network that is underlying this situation. And effectively, if you go back one step and you take a look at the relationships across these people, you find out that these are the relationships. Each one of those car accidents, again, that are apparently isolated, and two extended families that are connected by a number of links, and they are owning some property together, and they are connected by perhaps some other relationships. And now, every one of those random accidents happening at about the same time are really part of a fraud scheme that is trying to make money from the insurance companies. They were staging the accidents to get them to pay those claims. This is a little bit of what you get when you have additional data elements that you didn't have before. Insurance companies normally would have this set of elements. They know about the accidents, they know about whatever is in the police report, but they may not have information about the underlying social structure. One of the things that we do, and this is done with the technology I'll describe, is build a complete social graph of the US. And this is not built from social networking sources. We don't use them for a number of reasons. One is because we are very risk averse, and we try to ensure that whatever we use the data for is consented in some way, or it has, of course, all the permissible uses. So we refrain ourselves from using data from Facebook or anything like that. We build this from public records. We build this from data that's available from motor vehicle divisions in the different states, from perhaps utility companies and utility bills, and other information that is available publicly. But the interesting thing is once you build the structure of the social network and you superimpose to that structure some, in this case, apparently random events, you find that there is some methodology, some consistency across, and that are no longer random. We'll see more examples in a moment. That's another one. Again, I brought a few of these on fraud because I think fraud is sometimes is representative and it's easy to understand and to know what the relevance is in this type of analysis. In this case, this is about property, real estate flipping. People that buy houses and sell houses for a profit, which is okay as long as you are not trying to defraud someone by doing that. And one way to defraud someone would be to have a number of people that are in collusion and buy the property and sell the property at a higher price. And of course, the bank that generates a mortgage for that property would be absorbing the extra price. And that person could sell it to someone else for a higher price. And this can inflate the price of a property. Keep in mind the price of anything. The price is a contract between a seller and a buyer, and it's just an agreement. So it is semi-artificial. And you normally base the new price of a house on the price of the previous transactions on that house. So if you have enough number of people that are apparently disconnected and they buy and sell the house and the house price goes up and up, at the end of the chain, you will find a fool that will buy that house for the next higher price, and you just go away and get a significant amount of money over the price of the original price that you paid for the house. Of course, all this in collusion, and this involving a number of people, connected or not, in the more traditional way of seeing a social graph. But at some point, they are connected because they are connected by moving houses. So a connection could be represented, and this is how many of you are familiar with graphs? Graph theory, I assume that a number of you, very good. So the edges don't need to be human relationships from the standpoint of a family relationship. They can be a transaction. If I sell you something, well, we are connected in some way. It might be a weak connection because it was just one time and it was just one thing, but it's still a connection. So things that we are looking, in this case, to identify the fraud is, well, we have a social graph of the entire U.S. We have also information about real estate transactions in the entire U.S. Now, with this information, can we look for properties that have been flipped several times in a short period of time, that flipping generated profit, the delta between the original price and the end price, and this correlating with individuals that were connected in some way, perhaps through several of these transactions. Once you define what the variables are, assuming that you can do large-scale analytics and take the data from the entire US, and just to give you an example, you can see that this represents about 700 million deeds over a relatively short period of time. And when we do this analysis and when we build the social graph of the US, at the peak of the process, we process about 700 to 800 billion attributes on entities there. And the entities are about a couple billion. This accounts for people that are alive and also deceased people. Well, if you can do all this, you might be able to focus you have the graph, you have the dimensions, the features that you're trying to find correlation for, and you identify sections in the graph that have a good alignment of these features, and these are flagged here. You might not be able to see them clearly from there, but essentially the profit, the connection across people, and the frequency of the flipping, the times that it was flipped in a short period of time. Now, if you do that, and you look for areas in the graph where these three dimensions align, you may find a few of those, and if you rank them, you will find the one that is the most common, well, perhaps the one that law enforcement should focus on first. And if you drill down, you can see that there is in this particular piece of the graph, in this subgraph that has a number of these, you see a person in the middle that himself has some of these properties flipped on his name, but has a number of others that are not flipped on his name, are flipped on the names of associates, people that are connected to him, but are not him, of course. If you are doing this, you want to fly under the radar, so you will try to find other people that you can recruit for this goal and potentially pay them as well.
So what would be the relationship, for instance? Is it a family tie or is it something else?
It is all over. How this is, when we did the analysis over time, how this started is, well, he started doing a few of this on his own with a few friends and close family. Eventually, this became a large-scale business, so he started recruiting people. And many of those were immigrants or people coming from other countries, and that didn't. When you did a deeper analysis, they even didn't have the mediums to be able to buy those houses. So the banks were approving these mortgages because he also got some agents in the bank that were on his side, and real estate agents that were on his side. Of course, the things that you need to pass when you're trying to do this type of transactions are, for example, the appraisal from the bank. The bank will come and say, hey, this house is not really worth this. So he might need to have some links with some appraisals and ensure that in those banks he will get the approval for the mortgage.
Yeah, but what is the specific, for instance, piece of data that would connect this person with someone on the edge over there? Is it the employment records? Is it something else?
It could be any of those. It could be any of those, and including the transaction itself. If this person buys this house and sells it to this person who sells the house to this other person, who sells the house to this other person, well, all these people constitute a part of the graph. They are connected by the transaction, the specific transactions that they have in between.
So you can actually drill into those edges and find out what these things are?
Correct. Yeah, when we build these graphs are directed graphs, and they also have edges with attributes in those edges. Not all edges are alike. One edge could be a family relationship, another edge could be a transaction, another edge could be a co-ownership of some asset, another edge could be the correlation on living at the same place at the same time. There are a number of properties that we use across the edges to find relationships between people.
And the reason I'm asking that is because, there was a study that showed that, everybody knew everybody else within 6 distance.
The small world theory, yeah.
Where the small world actually starts interfering with the data, and everybody comes under suspicion simply because that's the way the world operates.
That is very true. And while that's true generally, and it seems that human society fits this small world theory, In these particular cases, what you are looking for is also some correlations on the other dimension. So okay, yes, these people are connected, but if eventually anyone would be connected to this person in 6 degrees of separation, if you take any potential edge across the graph. But if you are looking for edges that are interesting to this particular problem, for example, houses that have been flipped with the profit, well, that gives you a little bit more certainty. Of course, there are edges that might be weaker than other edges, and it's essentially your part of the analysis to define which ones of those are relevant to this particular problem.
So you used the word cluster at the top of your slide. Are you
Yes.
running a clustering algorithm?
Well, in this particular case, we have a number of algorithms, and it is a clustering algorithm from the standpoint of the type of algorithms that run. It is not your typical k-means clustering or hierarchical clustering, but yes.
Okay.
Yeah, but there is more than just clustering. Clustering is the algorithm that helps us find the proximity across entities. But there are a number of other things that, of course, are required to specifically build this type of representation of this problem. But yeah, we will get into clustering once we get into the technology. Okay, good. So eventually this person was this guy, here, Ray Gallo. He's now spending some time at the shade of a nice prison somewhere.
One thing I was hoping to catch is some kind of insight as to how you can differentiate between fraudulent transactions and somebody who's just good at selling real estate. I mean, what was it that keyed you into this being a fraud?
Well, in this particular case, the fraud aspect of it is the fact that they are trying to improperly profit from someone by pumping artificially the price. This would be equivalent if some of you are aware of some of the stock pump and dump type of schemas where people recommend you to buy some penny stock and they pump it and then eventually they dump all the stock that they have and then you're screwed. Well, that would be equivalent to this type of fraud. But of course, there is a point where you need to put some judgment on how far you can go. And we were talking just with Dr. Wook on this one. If you don't put proper judgment across it, you could essentially bring every U.S. person that ever sold a house as part of the scheme.
Are you doing that judgment mechanically in the system, or is that a human being that's looking at this judgment?
You need both. You need both. We do a good chunk. All the building of the graph, all the pre-filtering, looking for interesting areas, is done by the system itself. But the judgment call, it needs to be done by a human being, at least today. Someday maybe machines will be better to do that. But for now, it is human beings. Yeah. Yes, sure.
Do you consider this analysis as the foolproof method, or after getting results from this graph, you go in the field and check for the reality? Well,
you need to. And you can't, and I don't think any court would accept this as the only way to validate that these are criminals. So they will be looking for evidence after the analysis. But the analysis at least will be narrowing down what they cannot just go and try to find evidence on 350 million people. They can go and find evidence on 20 people if those appear as the high likely people of doing this type of things.
So even if your system shows some of the good ones as the fraudulent ones, because there are obviously weak relations also and you plot them, so still a further investigation might reveal that they are actually not.
It is always, again, there is always a judgment call, and it's always the way justice works. Right? Law enforcement will need to identify enough evidence to build a case on this. In this case, well, the person in the middle of the cluster, this person here, was that one person here. So I think they quickly made the connection there, and they quickly identified enough evidence in the way, and I think his fraud went beyond the equity stripping fraud, because he was also having some additional immigration fraud and other things in order to fill the blanks to be able to do this type of fraud. So, but yeah, it's always a.
What kind of graph database did you use for this?
I'll get into that in a moment. Yes, and I'll try to cover the technology part of it. as soon as I finish with some of the initial examples. I don't want to derail this piece. I'll get back to the graph. This is another one, and I'm bringing a lot of these things around graphs because I think also they are interesting nowadays, and people quickly identify graphs with some of these particular problems. In this case, this is a slightly different type of analysis, and this analysis is going to show you that sometimes you have hypotheses, and you go through analyzing how that hypothesis hold. And as you do that, you might identify additional hypotheses. And you can go back and, again, repeat the cycle to now use the new dimensions or features that you identified as correlated with the issue to expand your analysis. I'll give you a little bit of background information on this one. And this is also important, this background information, because it helps you also understand that many of these problems require domain expertise. You need to know what although all these things are executed by machines, the initial stating of a problem and the initial hypothesis generation needs to be done based on the particular problem domain. And so far, it's something that requires humans as well. In this particular case, we are going to talk about drugs. And this is drugs that you can buy in a drugstore, and that many of those you get prescribed for some disease. If you look at drugs in general, you can potentially classify them based on their distribution. If you have a social graph, there are certain drugs that have a penetration that is more broad across sections of the social graph than other drugs. And it makes sense. If there is a family disease, let's say some high cholesterol type of disease that can be transmitted from parents to kids, well, there is a high chance that in that family, many people will be receiving the same type of drugs. Right? And that's normal. There are other drugs that are prescribed for a particular reason to a single person, but there is no reason why other people in the family should receive those. So you have drugs that, if you graph the distribution across a social graph, they will have long tails, social drugs, and there are other drugs that when you look for them in the social graph, they will just be point blank in some individuals and not in others. Well, there is, in this particular case, one drug, which is Vicodin, is a potent painkiller, which shouldn't be presenting any social distribution. You wouldn't expect a long tail. If you have had surgery and the doctor gives you Vicodin, well, it gives it to you, but there is no reason why your siblings should have Vicodin too, or your parents, or your friends. So if you do this analysis, and we did it again, across we had a certain amount of data on prescriptions of Vicodin that we were trying to do analysis on, and we again superimposed this on the social graph of the US for these areas that these transactions represented, and identified prescribing doctors and also dispatching pharmacies, those that are fulfilling those prescriptions. Well, when we started looking for cases where the distribution of the drug was social, in which of those subgraphs, we identified some subgraphs that had an abnormal social distribution of this drug. And we started looking at the prescribing doctor, which ended up being always almost the same for the same subgraph. And the dispatching pharmacy, which ended up being almost always the same as well. But as we did that, we started seeing that there were other dimensions that also correlated with this particular type of subgraph. One of those was the distance between the doctor that was prescribing this and the pharmacy that was dispatching it and the person that was receiving the drug. These people seem to like to drive, and they end up driving like 30 or 40 miles to go to the doctor to get the prescription, and then another 30 or 40 miles in a different direction to go to the pharmacy to get the prescription fulfilled. And it tends to be the same doctor and the same pharmacy. So now you get two additional pieces of information that you can use for your next analysis. Now perhaps your next analysis would be, okay, how many people drive 30 or 40 miles to go to the prescribing doctor and the pharmacy, and is that correlated with some non-legal activity on drugs? In this case, obviously, they were getting these drugs to then resell them in the black market. But this shows you how you can iterate in this type of hypothesis generation and get deeper and deeper looking for potential cases that fit your pattern. So far, so good, right? Good. But again, not always about people, not always about networks, and well, at least not graphs. In this case, is another one, and this shows you a little bit of what having a lot of data and having the ability to process a lot of data gives you. This was done for a government entity that needed to identify if their data was being extruded, leaked from their network. And not just leaked inadvertently, but leaked by some well-defined threat outside. So the issue with this type of leak is that it's normally not done in just one shot. It's not that they go compromise a machine and extrude all the data they can, because if that was the case, it would be very easy to detect and block as it's happening. Unfortunately, what they do is they compromise the machine, they leave that machine compromised, and over time they extrude the data in small drops, which if you try to do point-in-time analysis, you'll probably not identify it because it will be under the level of noise. You have so much noise, so much network flows in the network that identifying this particular flow that is extruding data might not be as apparent, particularly if the external IP address or the external destination of that data is not necessarily in a black list. But if you look for this type of pattern over time, if you can correlate this in a long period of time, now this periodic activity starts to appear on top of the noise, the level of noise. Well, now you have, if you correlate in the time domain, those things that correlate because they have a defined frequency will appear more relevant over the things that are more random. And this is a good analysis that gave some good results. It's still, I think, in production, in use. And showing, this is just a representation of flows. Of course, this is not real data. But some flows deviate from what you would expect, and the size of the bubble and the distance from the norm are indications that that could be something to look at. Again, does it require a human to look at it? Yes, of course. But the human, and I firmly believe this, the human brain is great to create things and to do apply judgment and to do analysis in a relatively small scale, but perhaps deep analysis. But there is no way a human could go through billions or trillions of flows and identify which ones are the relevant ones. So that's exactly what computers are good for. Yes?
So I'm concerned about your result, but was this model as a graph problem, this problem?
No, this is, well, you can almost express anything as a graph problem, but this is not. We didn't express it as a graph problem.
Okay, because I'm looking at, if you have this kind of huge data you can't fit in memory, and the locality is destroyed when it comes to graph. So you can't have this.
You just touched on something that I will say in a few minutes, but that is a great point. A graph, representing a problem as a graph, as an abstraction, in order to understand the problem, I think it's quite natural. But sometimes trying to naively port this representation directly into the machine creates severe problems, and those problems have to do with locality, with the fact that a graph traversal algorithms require a lot of indirection, and that indirection, if it's translated into 6 in the drives, kills the performance, makes it possible. And some problems become intractable if you're doing that. And also that if you try to partition your graph, you need to now reduplicate sections of your graph across different machines because there is no clean way to partition the graph. In which dimensions do you partition the graph? And I'll go back as how we process graphs, which is slightly different from the traditional thing. This is not done. None of the things that I mentioned are done in any graph databases. These are not triplets databases. These are based on our own data processing engine, and I'll explain some of the basis behind it. But yes, we can partition these graphs. We don't represent them as a graph. And we can also run them from hard drives. We do a lot of heavy lifting at data build time to denormalize certain properties of the graph, so that when we need to do retrieval, we can do a retrieval in an O1 or O log n operation rather than on a whatever, quadratic or worse. But we'll go back in the, that was a great question because that gives a segue for the next section. Other few examples, and this is, every one of these I mentioned in every one of the cases is built on our HPC platform, and I'll get into that in a moment. This is just using public data, and this example is available from our portal as well. If you go to hpcsystems.com, this entire example and all the source code for it, and the data, of course, is public data. This is building a Wikipedia PageRank algorithm in ECL. It's just a simple example, and people are familiar. Who is not familiar with PageRank? Okay, who is familiar with PageRank? Everyone? Okay, very good. Okay, great. Then we're, yeah. So this is an example of building an iterative algorithm in ECL, and I will mention later why this is interesting. This, and again, this can be done in just a few minutes in even a small-sized HPC system. This was another demo, and for whatever reason I missed. I'm not having the screenshot. This was just doing log analysis again, relatively large-scale log analysis, taking all the Wikipedia logs and processing them in a relatively small HPC system to do some analysis on temporal analysis on web page access. Some simple examples. These are all available on the portal. If you want to get familiar with some simple ECL code and working examples, the demo is available and all the code is available. Yeah, sure.
So when you say relatively small HPC system,
well, a small HPCC, and I'll go back there in a moment. HPCC as a platform is designed to work in essentially any size cluster, from one virtual machine to hundreds or thousands of nodes. It all depends on, and it has two components, and I'll go back. Let me get back to that in a moment, and I'll explain how you do some of the performance analysis on it. So, going back to the general process in big data or data that is big enough, you get a lot of data, and that data might be structured or unstructured, and yes, you might have your say when I say unstructured, because you say, well, even human-generated data is structured by the grammar of a language, but you know what I mean. Yeah, that grammar might be difficult to define, so let's think of it as unstructured. And as you move from the left to the right in this graph, you will see that the volume of the content decreases because you go and cleanse the data and normalize the data, translate it into formats that are easier for the machine to handle, and reduce the size, the overall size of the data. But the value, the information that you get from the data, it grows and grows as you move. As you link the data, and linking data is a quite critical operation, particularly when you have a large number of diverse data sources that can be linked in some way. You extract additional information that wasn't necessarily present in any of the data sources, and it was present in the relationships that you're building across those data sources. Some of the examples that I gave you before are really viable just because you can build those relationships, and I'll go through that process in a moment. But eventually you end up with something that is this. It's fusion data. It's data that is now linked, data that now acquire different meanings just because of these relationships. And now you can build your analytical algorithms and you saw some of those before. You saw some of the examples in clustering and link analysis. I always, perhaps it's my reductionist view of things, but in my mind, the end goal of any analytical process in data is to sift through petabytes of data and reduce all that data to 1 bit. Yes or no? Is this good or is it bad? Is it expensive or is it cheap? Well, maybe not 1 bit, maybe a few bits. But knowing which bits are, and particularly being able to beat the randomness, essentially, well, if you just say that it's always 1, the bit, you have 50% chance that it will be correct. But beating the odds in the randomness, essentially making a bit that really has a meaning, is where all the expertise and sometimes the art is. And we'll go to that. Now, the platform that does all this for us is our technology platform, and I will go through this platform in the next slides. This entire platform was released as an open source project in 2011. We built this platform, we designed it originally in the late 90s. We built the platform from scratch. We were one of the first companies to build a distributed data processing system when we were trying to convince, well, someone would come and ask me, hey, why are you doing this? And I would say, well, because this is the only way to scale out, and this is the only way to make some problems tractable, which are not tractable in traditional databases. And, of course, they would always come back and say, well, why don't you use database XYZ, which does this? And that XYZ would be Oracle or Sybase or Microsoft or whatever you want. But, of course, we knew that it wouldn't scale. We got to a point where we couldn't buy any larger server than we were buying, and they were still very expensive, and still we couldn't process the data in the time. So we were dropping some data on the floor just because we couldn't get the data into the system on time. So we built a distributed data processing platform. We believed that it was our core technology, our core IP, so we didn't want to make this available to anyone. And we did sell several of these platforms as appliances for the most part, mostly to either large companies or government agencies that were coming asking for them. But we were never advertising them or pushing them out. Eventually, we realized that the platform itself is really plumbing, it's infrastructure. The real expertise is on the algorithms that we build on top of it. So why not releasing the platform as an open source project? And I've been always convinced that the open source model is good, and I can explain why we thought it was very good for us. And we eventually ended up taking the decision and releasing this open source. And then an Apache 2.0 license, so anyone can use it, anyone can fork it, clone it. The source code is in GitHub. We release binaries with every minor and major version for the most common Linux distributions. This runs on Linux, so there are no strings attached there. And of course, we love to get contributions and comments and new use cases because that makes the platform better. And that is our ulterior motive. We are not there to make money in selling the platform. We are there to improve the platform. This platform is the core of our data services. And we make $1.5 billion every year just in LexNexus resolutions in data services. And if we can make the platform 10% better, that can make our data services perhaps 10 or more % better. So the better the platform is, the better we are. Okay. And some of the things that I mentioned before, one thing that is interesting piece of a fact is that we developed this platform before ever anyone spoke about MapReduce as a distributed data processing paradigm. Yeah. For those, how many of you know Lisp? Okay, there you go. Very good. Okay, we have this one. For those that know functional programming, operations like mapping and reducing or folding have been known for 50, 60, 70 years. But applying them as a paradigm to do distributed data processing was something that a couple of Google researchers published in 2004. When we built this platform, it was even before that. So, of course, obviously, the platform is not based on that particular paradigm, although you could say that generally speaking, almost anything can be done with map and reduce. At the time we decided to do this, we decided to go with the data flow type of paradigm. Data flow paradigm is also a declarative type of paradigm where you define things by what they are or what you want to get done, and the system will generate the code, the imperative code that tells the processor what needs to be done, in which step, and how. How many of you know SQL? Very good. Well, SQL is a declarative programming model. So you tell the database what you want. You don't tell the database that what needs to be done step by step in the tables and looking for the keys and iterating or anything like that. And you don't care if the table is stored in whatever format it is, or it's processed by whatever processor you have. The same thing you do with our programming language. We'll get into that in the next slides. So, okay, so let's do a little check here. Are we good? Yes, we are. Okay, good. So, when we built this platform, we had a particular set of needs that had to do with, on one side, data integration. Data integration is a process by which we receive data, tens of thousands of data sources, and integrate them into a cohesive and consistent linked data repository. And analytics. So we would also perform certain analysis on this data to do things like the ones that I shown before. On the other hand, we had the need for real-time delivery of data. the needle in a haystack type of search, plus real-time analytics. I have all this historical data. I will train a classifier with this historical data. This is large-scale batch-oriented processing. But once I get the coefficients from the classifier, I will put those coefficients in a real-time system to do real-time classification. See, these are two different types of approaches. And it required us to build two different types of systems. One is called Thor. Thor, like the guy in the movie, the Nordic god of thunder with the big hammer, is the big data processing engine. The delivery system, the real-time delivery, is called Roxy. Both are based on a distributed platform. Both are based on local storage. The data is partitioned across the systems. Of course, you don't need to be concerned, or you don't need to be even aware of how the data is partitioned. The system takes care of all this for you. You don't need to be concerned about the parallelisms. The system takes care of that for you. You don't need to be care about racing conditions or parallel programming or anything like that. We built a higher level language on top of it, which is this ECL language that makes all these things implicit. You tell the system what the data needs to do at each step in a data flow paradigm, similar to what we do with SQL, more or less. SQL, the issue with SQL, and we looked at SQL back in the day, is that it makes it very difficult to do structured programming. And your programs can be unwieldy over time. Particularly it doesn't allow you to do proper code reuse. It doesn't give much encapsulation. So it becomes complex. And it was built as a query language. So when you try to express data transformations in SQL, it's so we built this language. We also opened this language. The language is completely released. We didn't go for an ANSI standard because the process is extremely long. But we did release all the specifications of the Creative Commons license if anyone wants to implement ECL in whatever, any other environment. It takes lessons from modern programming languages and functional programming languages as well. Things like lazy evaluation, things like encapsulation. And encapsulation not just of code, but also of data. And data encapsulation is critical in big data. When you are trying to apply an operation on a data set that is large enough, and you are browsing the data set from beginning to end, you want to browse it once. If you need to apply 10 operations, well, you better apply them together. Because going back to that data set is spending a lot of time. And moving the code to where the data resides and providing all the internode communication that is required for certain algorithms. The most basic algorithms, when you're trying to build an index on a data set, one of the first things you need to do is sort. And the same thing when you're trying to do a join. Well, sorting data distributed in a system means that you need to exchange data pieces across the nodes. And the system will do that for you. But it will do it in a way that is even smart. We support different sorting algorithms. To give you an example of where smart comes to, is if you have data that is not uniformly distributed over a key, and typically is names on a phone book. Well, in the US, there are a lot of names that start with A and B's, but maybe there are not that many names starting with X and Y's. So if you were to use a typical radix sort, how many of you know what a radix sort is? This is good. Everyone knows almost everything. Okay, good. So if you try to use a radix sort, it will distribute the data uniformly over that key space, which will end up having some nodes overloaded with data and some other nodes with very few records. This is a data skew, which is important because your system is as fast as the slowest node. Well, our sort algorithm will go there, we'll build a histogram of distribution in each one of the nodes, we'll define what the partition points are, and then it will start a sort. Taking these little steps before, and this is all done implicitly. Again, you just said sort. This is a sort in HPCC. It's just a single sort instruction. The data set, the key, and then some additional attributes if you want. One thing that is important before I move to the next slide is that ECL compiles into C++. And the team, when we were looking into doing this, we ended up hiring a team of developers that came from a company called TopSpeed. TopSpeed developed a 4GL language back in the 90s. And some of these guys came from Borland. How many of you have used Borland compilers? Yeah, there you go. Yes, I did too. So, well, these guys were the ones developing Tour Pascal back in the day. And Sidekick. How many of you know what Sidekick is? That's an old Sidekick. Oh, that was an old terminate and stay resident utility for DOS that had like a little phone book and other things that salespeople were using back in the day. Well, one of those developed this Sidekick back in the day, but obviously it's not very popular now. And this is how they look like. And this is obviously a very high-level view of them. And some of the things that they do, I'll go into some additional detail later. This is how the architecture of the system works. Thor and Roxy both work seamlessly. Data that gets into Thor can be processed, can be indexed, and these indexes can be deployed into Roxy. These indexes are a special type of indexes. Roxy uses a distributed B-tree type of index to be able to leverage distributed data. The data will be distributed across all the nodes when it gets to Roxy, and it's compressed and has special formatting. But the indices are these distributed B-trees that allow each node to operate semi-independently. And we have a quite a good amount of work into minimizing the amount of intermediate result candidates that we get from the different nodes. And other sophistications on the way we handle keys. These are compound keys. These are not just simple keys. It's not just a key value store, and it has the ability to skip portions of keys and still be efficient in the retrieval process and others. So there are a number of sophistications there. Again, all the source code is available, so you can go and check it yourself if you like C++ and like to take a look at it. Of course, all this programmable by ECL. Low level. This is no different from your typical Hadoop cluster, if you're familiar with Hadoop. And Thor, same type of setup. Roxy, though, would like to use better performing drives than normal SATA drives because it's doing indirection. I mentioned before that in Roxy, we have these B-trees, and B-trees means that you're doing 6 on the drive. So if the drives in your Roxy would probably be better if you had SAS drives versus SATA drives, or SSDs versus mechanical drives. But it still works either way. Yeah.
So when you're talking about the Thor, you mentioned that the building B-tree process. Are you building the B-tree is a distributed pattern or like a single one huge tree?
It is distributed. The B-tree that is built, and I'll go a little bit into more detail on this one. In Thor, when you say I want to build a key that I will use for data retrieval on Roxy, you tell it, well, just key build. That's a single sentence, right? That takes care of it. But individually, what the nodes will do behind the scenes is, of course, sort the data if it wasn't sorted, and lazy evaluation takes care of that. If it was already sorted, it won't sort it again. And it will identify the partitions that will be required for those nodes, and then it will build the B-tree. That will have, at the top, obviously, a single entry. Your root is just one root. It will have a next layer that of entries which will indicate which node contains that piece of that partition of the data. And then it will have the data in the leaves of the next level. Which means that when you tell Roxy, go and pull my keys from Thor, Roxy will be able to go node to node, even if the number of nodes don't match. If you have 400 nodes in your Thor and 100 nodes in your Roxy, well, Roxy will know that it needs to go with one node and pull from 4 nodes in Thor to get those partitions. But the data will be already partitioned and, again, lempel-zip compressed into the leaves of that B-tree. And in Roxy, every one of the nodes runs 2 subcomponents. One component is called the farmer, and every farmer gets the identical portion of the top level of the B-tree, which is very small. It's just indicating which nodes, which slaves will have the proper partitions for the particular problem that you're trying to address. And then it will have, for every one of the slaves working on Roxy, the partition that corresponds to that particular node. So when you send the request to Roxy, the request can go to any node. Any node runs the farmer portion. Now, the node will have the information about where to send that request to get the proper data. And that is, and now going to, again, a little bit more detail, it's done over a multicast. So every one of the slaves subscribes to a multicast channel, one or more multicast channels, depending on which partitions they have. And the farmers will know where to send the request in those channels. Of course, for redundancy purposes, and Roxy can be configured with any degree of redundancy that you want to configure it. Particularly for production systems, you might want to have more than one copy per partition. Well, there will be several slaves subscribed to a particular channel that will represent that partition. If you have enough number of queries, every one of those slaves will be active. So the more copies you have of your data, the faster or the more queries you can respond to at the same time. But even if a node fails and you lost a copy of your partition, the other nodes will still be able to respond for that copy, so you still have your data intact. If all the nodes fail for a particular partition, well, you can define if you want Roxy to stop, or you want it to continue but not respond to whatever was in the partition, so that data will be lost. But again, redundancy is key there, and there is no single point of failure. In Roxy, once you deploy the data, there is, well, the only single point of failure really is the switch, the network switch. If you have only one network switch, of course, if that fails, you better have two Roxys. But other than that, any node can fail, any other part can fail, and there is no special system there. There is no central controller, and there is nothing that can really make the entire cluster fail. And the queries are just sent by a dump load balancer, just round robin the queries to any Roxy. I'm not going to go into the details on ECL. You can see we have something that is called a playground, and this is online as well, that allows you to do web-based ECL programming and runs on a query, runs on a cluster behind the scenes. So you can play with ECL. It's a declarative programming language. Keep in mind these equality signs. These are not assignments. These are definitions, similar as in Lisp or Haskell. How many of you know Haskell? One. Very good. Okay, good. Two. Good. I like Haskell, by the way. But anyway, so they are definitions, and variables are immutable. So perhaps variable wouldn't be the right name to give them their attributes really. And you build using a bottom-up approach, similar to what you do in other programming languages, where you define small things and you go up, or just define the overall process and then start going down and building your functions that will represent each one of the individual capabilities. Well, I don't know what happened with my machine learning. And we're getting more into the applied side of things in HPCC. In ECL, it's a general programming language. You can build really any algorithms. We have a number of algorithms for machine learning. We built an extensible library that allows you to do some of the most common machine learning methodologies with just pre-built ECL code there. If you want to use a classifier, we have a number of classifiers available. Regression, we have a number of regression algorithms available as well. Clustering, we have the typical clustering, and this we have k-means, hierarchical clustering, and others. And of course, we have also analysis of distributions and other things. So if you want to build a distribution, we continue to enhance this. One of the things that we have done lately in the last year and a half or so is to add BLAS underneath HPCC. How many of you are familiar with BLAS? Very good. Well, it's always the same hands. Very good. So BLAS is a high-performance linear algebra library to specifically deal with algorithms that require, again, high performance and is in vectorized type of implementations of algorithms where you need to do matrix vector operations. So we built support for BLAS, for PB BLAS, which is parallel block BLAS. So you can partition your matrices, and you don't do it, really the system does it for you, and distribute these matrices across the entire cluster, and then you can process in parallel across all the nodes in the cluster. Not going into all the details, just keep in mind there is a lot of this. This is all available. It's all open source. Just feel free to go, drill on the code. We have also, I didn't mention before, we have two things that I think are important resources for you. One is we have a set of forums and distribution mailing lists that you might want to subscribe if you like the topic and want to do a little bit more digging on it. The other thing that is quite useful is we have massive open online courseware on HPCC, on ECL, basic and advanced ECL. We have all the basic courses free for everyone. We have the advanced normally paid for, but of course, not for our academic partners. So feel free to go, and if you need, we can give you all the free access to all of these courses. So, and this includes not just the videos for the training, but also all the synthetic data generation, all the quizzes, all the exercises, the testing, and of course, anything that you need to ask, you can use the forums, and we'll be always eager to respond. I think this is good because it can get you to learn the platform in relatively short time from the comfort of your couch. You need to go. That's a good thing. Yeah, it's cool. Before we used to do only face-to-face training, and it didn't scale. There are so many trainers you can have, and you can. And they believe me, they really go around the world, but it's a never-win situation. So doing this online simplifies things, and we are now building more internationalization and localization in these courses so that people from other countries, other languages can still take advantage of them. We are doing some Chinese translations on some of them. I did mention that, but the platform also supports, it supports UTF characters, and we are building actively specific support for other languages. Ideogrammic languages, and I mentioned Chinese, are particularly challenging when you are trying to do analysis, NLP, natural language processing, because, for example, they don't have any separators across words. There are no spaces. So you don't know that a word has 1, 2, 3, 4, 5 characters until you understand what word you're talking about. And if you didn't do the parsing correctly in the first word, the second word will have no meaning whatsoever. And that's, Chinese people must be very smart, but it's hard. So we are building support for word segmentation, which is this particular problem, and there are others in other languages. So we are actively trying to get better and better at supporting international communities. More stuff on our ML. This is important, and I sometimes like to remark this. When you're, and we all get lost. As you can imagine, I'm a buff of algorithms, and I love machine learning, and I get into these algorithms and these discussions about if I should apply this particular classifier or this other. Well, if I have a small number of training cases, then I probably need to use a naive-based classifier. But if I have a lot of them, because it converges faster. But if I have a lot of them, then I probably want to use logistic regression because it has a better precision and recall. But at the end of the day, if you didn't do your homework first, which means if you didn't go through the process of cleaning the data, understanding what the data was, normalizing the values, standardizing them, and linking the data, no matter what you do, it's useless. It doesn't matter how good the machine learning algorithm is. If you didn't do your homework before, that doesn't do any good. And this normally takes 85% of the work. So and this is important, if you're trying to do all these things in one platform, let's say that you say, well, HPC is great for this. So I'm going to do all this in HPC. But now I'm going to move all the data out of HPC to put it in some other platform to do the analysis. Well, you are in for a ride because it will take you quite a while to move all the data out. You better have something that can do both things in the same place. That's quite useful, believe me. It has been one of the keys of success on our side.
But do you have like visualization as part of the system and define input format? Do you require certain input format, or you support, let's say, something like CSV or something?
Those are great questions. First of all, yes, we do have visualization, and from within ECL you can drive charts. And we are building now graphical dashboards that will be also released open source. The code is available already, but we are trying to package them now. Complete a web-based dashboard system that allows you to put charting and other things and pull it from HPC. In addition to that, you can use any visualization system that supports JDBC or web services, SOAP, RESTful, JSON, and pull directly from HPC, from Roxy, from Thor. All these external formats are supported from the front-end interface. For data ingest, we do support your more common formats, CSV, of course. We support a fixed record length and fixed field length, of course. We support XML, too. Those are the basic ones. But even if you have data that doesn't have enough structure to be able to be defined in any of these formats, you can still pull it in and then do the parsing in ECL. That's what we do for the most part. Well, imagine if you have text data. You have tweets, and those come in any random format. You will just say my delimiter for records is whatever, is the paragraph, whatever, the end of paragraph, or the end of tweet, or the next header. You pull the data into the system, and then you can parse it in any way you want. most likely that's what you want to do rather than try to parse your data before getting it into the system. Parsing your data in a single server, it's normally a hard thing to do, and particularly because in the system you can use ECL, which is quite good at doing this text parsing. It was built for that. This is another very cool thing, and I like to mention it as well. I briefly said that I believe that humans are good at thinking, but machines are good at doing things over and over. So when we find ourselves doing something more than once, we are convinced that we shouldn't be doing it at all. So we make the machine do it, and we move on to the next level of abstraction. So we build abstractions on top of the system as we define things that are better for the machine. We still keep ourselves at the judgment call or the strategy of the thing. So we built some of these abstractions, for example, for data linkage. I mentioned, well, data integration and data linkage is one of our core problems. And we're not going to be coding ECL over and over for these things. And this might be hundreds or thousands of lines of ECL. So we built an abstraction called SALT, Scalable Automated Linking Technology, that handles all the data ingest, all the data profiling, all the parsing, normalization, standardization, and linking. The other thing that we do frequently is graph. And again, this might require a few hundred lines of ECL. And why? Why wouldn't we have an abstraction that builds the ECL code for me? And this is what KEL is. KEL is no longer the future because we just released version 0.4 of KEL. KEL is a graph-oriented language, similar to ECL, that is a data-oriented language. And in ECL, you think in terms of data rather than underlying representations of the data. In KEL, you think in terms of graphs rather than in the underlying data. So in KEL, you define entities, associations, and queries. And the system takes care of the rest. KEL, the same way that ECL compiles into C++, KEL compiles into ECL, which compiles into C++. SALT compiles into ECL, which compiles into C++. And every one of these abstractions gives you a lift in the number of lines of code that you can create really in ECL by just coding in this language. In the case of ECL, you can, in the case of KEL, every line that you define in KEL generates about 10, 12 lines of ECL. And that generates another 100 lines of C++. So if you have a little set of a little KEL program or KEL definition of a graph that is, 20, 30 lines of KEL, you have now hundreds of lines of ECL generated behind the scenes that you need to work on and you need to maintain, which is more important. And if we find a way to optimize something, we put that in the code generator. There is no need to go and retrain every person about this optimization or this improvement or this bug fix. And there is no need to go back and fix the code in 20 different places to put that bug fix in place. I'll give you a little example there of what you can do. We are starting to publish a set of blog entries. If you go to the site, the first entry is already published. There are 3 more that are already written, but they are not published because we want to create expectations. We will publish them soon. So essentially, you define entities, and you define, in this case, it's from IMDb. So you define where they are coming from and what the UID is for those. You define what associations are. Co-star are actors that share a movie, for example. And then you define queries. I want to be able to find actors, connected to actors. And this is just the beginning. This in the version 0.4 deals with all the typical graph traversal algorithms. The next versions will start dealing with other things like, for example, centrality of nodes and other properties in the graph. We are just building one on top of the other, right? But interestingly enough, in KEL you define your graph, you define what needs to be done, but when the system generates the ECL code behind the scenes, it will try to do as much lifting as it can on the data generation side, on the store side, on the batch-oriented processing. So it can potentially denormalize a number of graph operations. And I will give you an example. And this goes to your, sorry, what's your name? This goes to your question before. one thing that you can do with graphs is represent them as adjacency matrices, right? Adjacency tables are well known. How many of you know what an adjacency table is? Good. So essentially, you have a table that represents the entities on one axis and the entities again on the other axis, and then you have numbers that represent the strength of the connection for those entities that are in just 1 degree of separation, connected directly. Very good. If you build this table for a graph, and you might not have a table, but you might have a more of a tensor when you have multiple tables for different type of attributes. That's valid as well. If you were, but let's think of a table. Let's say that you have only one type of adjacency. And now let's think that you want to know who is connected in 2 degrees of separation. A natural thing that you can do is to walk the table. Well, this guy is connected to this guy in 1 degree. Now, well, I look for all of them in 1 degree, and now I do, again, greedy search looking for the next degree of separation. But another, more practical way of doing it, again, leave graphs behind and now think in terms of data, I can do a self-join of the table. Or, in linear algebra terms, I can square the table. Just multiply the table by itself, and it will give you automatically a table that has 2 degrees of separation. Multiply by itself twice, and you get 3 degrees of separation. Now, you can take all those tables and store them in the delivery system. And each one of these tables takes the size of the original table. So maybe you double or triple the amount of space that you need. And these are sparse tables, so they don't take that much space. But any lookup can be doing all one operation. You just go and seek and get it from the hard drive. Now, you don't need these millions of RAM, these petabytes of RAM, and a single node. You can do this distributed across a cluster, and you can do this on disk. Now, your main problem, and disk is very cheap for volumes of data. So you can get petabytes of disk at a very affordable price, and the speed of retrieval will be a lot faster than even if you were going to RAM. So that's a different view. Again, if you take your graph problem and you move it back into data land, it makes it a lot easier to deal with it.
Are you going to RAM or you are going to disk?
You're going to RAM and disk. If you have it in RAM cache, that's good. If not, you go to disk. Again, well, it's not going to be an O1 operation because you have a bit tree, so it will be an O log n operation, but still log n is a lot faster than your typical traversal algorithm. There is a very good book for those that are also book buffs, as I am, which is called, and I have nothing to do with this book, I just read it. It's called Graph Algorithms in the Language of Linear Algebra. It was published in 2010 by a few professors from, I think, MIT and Berkeley.
Is that John Gilbert's book?
Yes, yes. Very good. That's a very good book. If you want to know more about these graph algorithms that are not graph algorithms, they are just linear algebra operations, this is a really good book. So essentially it translates this graph algorithm into the linear algebra you learned when you were in high school. It's a good way to take. Oh, very good. Yes. I won't go into much more detail. I just mentioned when I said visualization, if you don't like to write ECL, you can use things like this. This is called Spoon. It's part of Pentaho. It's an open source project that has a data workflowing engine. Well, this connects with HPCC, and we have all these modules there. So you can use this to define data workflows without even writing a single line of ECL. Not that you would do that, but if you like to do that, then it's available there. And I mentioned linkage. I mentioned SALT, in case you didn't know how SALT was spelled, Scalable Automated Linking Technology. This is not open source. This is the only one thing that I mentioned today that is not open source. It's a code generator for ECL. It deals with every one of the steps in the data integration process, profiling, parsing, cleansing, normalization, and linkage, and performs linkage using probabilistic record linkage. This is not your run-of-the-mill, your DATS rules-based linkage. Rules-based linkage is nice when you can define clean-cut rules and they work 100% of the time, which is not true anymore. Let me give you a simple example. You have 2 records. They have first name, last name, and city. And you say, well, if the first name is the same and the last name is the same and the city is the same, these 2 records must be referring to the same person. Well, the first name is John, the last name is Smith, and the city is New York. How true is that? Well, probably not. Well, if it's Flavio Villanustre in Atlanta, of course, yeah, that's true. And conversely, if there are typos, how do you handle those? So this uses this calculates the distribution table of or the specificity of the tokens and the specificity of the columns, the cardinality of the columns, and uses that information to calculate the strength of the links across those, and allows you to define the precision of record that you're expecting from that particular linkage process. But again, this is not open source, but if it's for research, we could make available in some way so that we can do also research on it. Some of the things on the linkage. And visualization. This is just for you, and I will finish it here. It's just some of the things that you can do. You can even use Excel to visualize. You can see how you can, even from Excel 2013 or whatever it is, Excel, you can just connect it to web services, to Roxy or Thor, and get the data visualized easily. Other types of translation. I'll stop it there. I want to go much more on this. We are already on the time.
If everybody could fold your sheets in this one for the raffle, did any student not fill out a sheet?
Let me see if I can get this slide there. Let me get this slide
I'll
there.
be on time. You'll be on time.
Right, getting there.
Almost okay. Just trying to get a...
To get up. I'll call it. You don't have to get up. Pass them this one. You don't have to get up.
to get back quickly to... This is some links that you may want to check if you want to learn more about it. If you have any issues to report, Jaira is good. If you want to communicate with the community, forums are a good vehicle, and decision lists are well. And again, all the code is in GitHub. Feel free to go there, clone it, fork it, do whatever you want. And if you need any help, let us know. I know that maybe going through a few million lines of C++ code might be challenging initially, but the code is, I think, pretty well organized, so it's relatively easy to understand. And you have binaries. We have binary packages for every Linux distribution, so you can just download those if you don't want to go through the source code and just play with it.
Let's thank Dr. Or would you like to take questions offline?
I'm sorry?
Questions?
Questions? Trivia. Okay, yeah, sure.
Test your balls.
Okay, let's see. Let's see how good of a job I did with this. If you get this one correct, you get a prize. Okay. 4. Very good. How about this one? Very good. Oh, wow.
He's the only one you want to use.
No, he didn't win.
You'll need coffee.
Sure.
Easy.
Very good.
That was you. Ah, there we go. Yes. She said.
Oh, very good. Wow.
This is tricky because you didn't really have time.
Oh, I didn't really go through the details. Okay, good.
K
K-means, for example, what else?
Marco, HMN.
No, Marco.
SVM.
SVM we do, yes.
And naive base.
Naive base, yeah, very good. Oh, wow, very good. Okay, good. Very good.
Thank you.
Thank you. What does SCALE stand for? No, you're very excited. No, you're very excited.
Knowledge extraction language.
No, close. He's in? Is it? Oh, wow. You are close. Okay, very good.
Okay, and we have the Kindle raffle.
Oh, yes.
Dr. Luca Roddy, want to pull a name? Sure.
I think she should.
Actually,
There's another one here.
Oh, yes. Oh, yeah.
Here. Now we need to mix them.
Mix them up now.
Make sure that you don't have your hand held inside there, and we need to.
Put your names in there early and often.
And,
They're nothing.
You know how it works, it's all the same name on site.
Yeah. I'll let you do the shuffling and then. Yeah.
Suspense. Chan chan.
We need the drums.
Yes.
Someone garage Virabudra.
Oh, wow. Very good.
Flavio.
I have 3 more cards if you want to raffle 3 more people.
Okay, sounds good, yeah. You have a smaller hand than mine. Well, like, if I put my hand inside, I might not be able to get it out again.
That's right.
And I don't want to buy it
Meet
for
our
myself.
opponent.
So,
Then I'll jump. One more?
2 more.
2 more. Just what did you run?
good.
Sindubala Ulapavadi.
Shiva.
Oh, she got one. No.
One more.
Let's get another one.
Xiao Chenzo.
That's good.
Yeah, he did. There you go. The lucky road.
Thank you.